Hello and welcome to this film, which is all about the ionisation of water. Now, this was touched on very briefly in the film about pH and pH calculations. Hopefully in this film we'll see how we can calculate the pH of a basic solution based on the fact that we know what the value of the equilibrium constant for the ionisation of water is. Okay, let's see what we mean by the ionisation of water. This is the reaction where water splits up into ions. Now, we've seen water in the past acting as an acid or giving away H+. We've also seen that when it does that, what we're left with is the OH- ion. So this is the conjugate base of water. We know that water is a terrible conductor of electricity, or we should know that from the bonding topic, which means that this equilibrium must lie way over to the left, that not very many ions form. But since it is a reversible reaction, we can write an equilibrium constant expression for it. Now, the equilibrium constant expressions that we've been writing in the SL equilibrium topic all concerned homogeneous systems where everything was in the same state. This is different. Here we've got a pure liquid and two aqueous ions. Now, clearly the concentration of aqueous ions can change. The concentration of a pure liquid does not change, and that means that rather than putting water on the bottom of this expression and its concentration, because its concentration is constant, we omit it altogether, and that's what our equilibrium constant expression ends up looking like. And we can give this equilibrium constant, which is called Kw just because it's talking about water, we can give it a value, and that value is 1 times 10 to the minus 14, which is a very small number, and this tallies with the fact that we know that hardly any of the water molecules split up into ions, because this product here of these two concentrations is tiny. Okay, now why is that helpful to us? Well, if we were asked to find the pH of a solution containing 0.01 mole per dm cubed of OH- ions, we might be struggling a bit because we might be thinking, well, hang on a minute, pH is the negative log of H+. And I don't know what the concentration of H+ is, but I do know what the concentration of OH- is. And hopefully it's not too hard to rearrange this and say that the concentration of H+ will equal 1 times 10 to the minus 14, so 10 to the minus 14, over 0.01, which is 10 to the minus 2, and so this must equal 10 to the minus 12, and since pH is the negative log of that, then the pH equals 12. So in other words, I can use this fact here, that the equilibrium constant for water is 1 times 10 to the minus 14, to calculate the pH of solutions even when I'm not given the concentration of H+ ions. Now, what happens with neutral solutions, or what are we talking about when we talk about neutral solutions? Now, in the past, we've talked about neutral solutions as having a pH of 7, or rather, in your previous experience of acids and bases, you might have seen them as that. Okay, but what we need to think about now is that a neutral solution, neutrality is less to do with pH and more to do with the relative concentrations of these two ions. So we can define a neutral solution as being one in which the concentration of these two species is the same. Okay, so not necessarily pH 7. You might remember that there are only certain things that affect equilibrium constants, right? So we can add acids, we can add bases, we can change the concentrations of things, but K shouldn't change unless the temperature changes. However, if we do change the temperature, we will change the value of this. We'll change the value of these two things here. Okay, now if you think about it, when the pH is 7, that means the concentration of H+ is equal to 10 to the minus 7. So in a neutral solution at 25 degrees centigrade, the concentration of OH- must also be 10 to the minus 7, and those two things multiply together to give you 1 times 10 to the minus 14. However, if the value of Kw is different at some other temperature, then in a neutral solution, the concentration of H plus will no longer be 10 to the minus 7 because these two are the same as each other. So let's just say, for the sake of an example, let's say I changed this temperature and it ended up being 1 times 10 to the minus 13. In a neutral solution, these two things have to be the same, and so the concentration of H plus would be 1 times 10 to the minus 6.5. Anyway, there we are. That is an introduction to what we mean about KW. In the next film, we're going to try and predict the pH of some solutions, since we're going to actually use this a bit more. But hopefully it makes sense, and hopefully if it doesn't, or if you've got any other questions or comments, you might come and see me or post a comment on YouTube.